What if the very building blocks of everything around us, your body, the stars above, even the air you breathe, were forged in the chaos of the universe's earliest moments? The story of the first atoms is not just a tale of science, it's the origin story of everything, from the tiniest particles to the vast galaxies. The universe's first atoms hold the key to understanding how we came to be. But how did these atoms form, and what forces shaped them into the complex structures we see today? In this video, we'll dive into 30 mind-bending theories that attempt to unravel this cosmic mystery. From the explosive birth of the universe to the subtle whispers of quantum fluctuations, we'll explore the ideas that scientists have proposed to explain the origins of the first atoms. Get ready for a journey through time, space, and some of the most fascinating scientific concepts ever imagined. By the end of this video, you'll not only understand the theories but also see the universe in a whole new light. So let's step back in time billions of years, to the very beginning where the story of the first atoms begins. Now turning to the first and perhaps most widely accepted theory, we explore the Big Bang Nucleosynthesis. Imagine the universe just moments after its explosive birth, a seething, unimaginably hot and dense environment. Within the first few minutes, the temperature dropped just enough for the first atomic nuclei to form. This process, known as nucleosynthesis, gave birth to the simplest elements: hydrogen, helium, and a tiny amount of lithium. These elements were the building blocks of everything that followed. Hydrogen, the lightest and most abundant element, made up about 75% of the universe's matter at this stage. Helium followed, accounting for nearly 25%, while lithium existed only in trace amounts. This delicate balance of elements was crucial, as it set the stage for the formation of stars, galaxies, and eventually planets. Without these first atoms, the universe as we know it simply wouldn't exist. But how did this happen? In those early moments, protons and neutrons, tiny particles that make up atomic nuclei, began to combine. The intense heat and pressure of the young universe allowed these particles to fuse, creating the nuclei of hydrogen and helium. As the universe continued to expand and cool, electrons could finally join these nuclei, forming stable atoms. This marked the beginning of a neutral universe, no longer dominated by a chaotic plasma of particles. The Big Bang Nucleosynthesis theory not only explains the origins of the first atoms, but also provides a foundation for understanding the universe's evolution. It's a cornerstone of modern cosmology, supported by observations of the cosmic microwave background and the abundance of light elements in the universe. As we move forward, we'll see how this theory connects to other ideas about the universe's earliest moments, each adding another piece to the cosmic puzzle. Now shifting our focus to the next chapter of the universe's story, we delve into the role of Quark-Gluon Plasma. Before the first atoms could form, the universe was a chaotic, seething ocean of quarks and gluons, tiny particles that are the fundamental building blocks of matter. Picture this, a universe so hot and dense that even protons and neutrons, the particles we now recognize as the cores of atoms, couldn't exist yet. Instead, quarks and gluons roamed freely, bound together by unimaginable energy. As the universe expanded and cooled, this quark-gluon plasma began to settle. Quarks, which come in 6 types, up, down, strange, charm, top, and bottom, started to combine in groups of 3, forming protons and neutrons. Gluons, the particles that act as the glue holding quarks together, played a crucial role in this process. This transition marked a pivotal moment in cosmic history, as the universe shifted from a formless soup of particles to a more structured state. This cooling and combining process didn't happen all at once. It took place over a fraction of a second, but it was enough to lay the groundwork for the formation of atomic nuclei. Protons and neutrons, now stable, became the building blocks for the first atoms. Without this phase, the universe would have remained a chaotic mess, and the elements we rely on for life, hydrogen, helium, and beyond, would never have come into existence. The Quark-Gluon Plasma theory not only helps us understand how protons and neutrons formed, but also provides a glimpse into the extreme conditions of the early universe. Scientists have even recreated this plasma in particle colliders, giving us a small window into what the universe might have looked like in its infancy. As we continue our journey through these theories, we'll see how this early phase connects to the next steps in the universe's evolution, bringing us closer to understanding the origins of everything around us. Now turning to the next fascinating chapter in our cosmic journey, we explore the Primordial Soup Hypothesis. Imagine the early universe as a bubbling, chaotic cauldron of particles, a dense and energetic mix where matter and energy were constantly colliding and interacting. This primordial soup was a state of extreme turbulence, filled with particles like quarks, electrons, and photons, all swirling together in a frenzied dance. In this chaotic environment, particles didn't just float aimlessly, they collided, combined, and broke apart in a constant cycle. Over time, as the universe expanded and cooled, these interactions began to stabilize. Protons and neutrons, which had formed from quarks, started to bond together, creating the first atomic nuclei. Electrons, once free to roam, began to orbit these nuclei, forming the simplest atoms, hydrogen and helium. This process wasn't instantaneous. It took millions of years for the universe to cool enough for stable atoms to emerge. During this time, the primordial soup gradually transformed from a chaotic, particle-filled broth into a more structured and orderly state. The formation of stable atoms marked a turning point as the universe transitioned from a plasma of charged particles to a neutral gas, allowing light to travel freely for the first time. The Primordial Soup Hypothesis helps us understand how the universe's initial chaos gave rise to the building blocks of matter. It's a reminder that even in the most turbulent conditions, order can emerge through complex interactions. As we continue to unravel the mysteries of the early universe, this theory provides a crucial piece of the puzzle, showing how the simplest atoms laid the foundation for everything we see today. With this understanding, we're ready to explore how the universe's rapid expansion during the inflationary period influenced the formation of atoms, bringing us closer to the cosmic story's next chapter. Now shifting our gaze to the next cosmic milestone, we delve into the Inflationary Universe Theory. Picture this: in the earliest moments after the Big Bang, the universe didn't just expand. It underwent an unimaginably rapid growth spurt, doubling in size countless times in a fraction of a second. This period of inflation was like a cosmic balloon inflating at breakneck speed, stretching the fabric of space itself. During this explosive expansion, the universe became smoother and more uniform, smoothing out any irregularities that might have existed. But how does this connect to the formation of the first atoms? Well, as the universe expanded, it also cooled, creating the perfect conditions for particles to slow down and interact. This rapid expansion set the stage for Big Bang Nucleosynthesis, the process we explored earlier, where protons and neutrons combined to form the first atomic nuclei. The inflationary model doesn't just explain the universe's smoothness, it also provides a crucial link to how matter began to clump together. Tiny quantum fluctuations, stretched by inflation, became the seeds for the formation of galaxies, stars, and eventually atoms. Without this rapid expansion, the universe might have remained a chaotic, uneven mess, making it far more difficult for stable atoms to form. What's fascinating is how the inflationary theory complements Big Bang nucleosynthesis. While nucleosynthesis explains how the first atomic nuclei formed, inflation explains why the universe had the right conditions for this process to occur. Together, these theories paint a more complete picture of the early universe, showing how rapid expansion and particle interactions worked hand in hand to create the building blocks of matter. As we continue to piece together the cosmic puzzle, The Inflationary Universe Theory reminds us that even the most dramatic events in the universe's history were part of a delicate, interconnected process. And with this understanding, we're ready to explore how quantum fluctuations played their part in shaping the first atoms, bringing us closer to the next chapter in this cosmic story. Now turning to the quantum realm, we uncover a theory that reveals how the smallest ripples in the fabric of the universe played a monumental role in shaping the cosmos. The quantum fluctuation theory suggests that even in the earliest moments of the universe, tiny, unpredictable changes in energy were already at work. These fluctuations, though minuscule, were like the first whispers of structure in an otherwise chaotic void. Imagine the early universe as a vast, bubbling sea of energy. Within this sea, quantum fluctuations caused tiny variations in density. Some regions were slightly denser, while others were a bit less dense. These fluctuations might seem insignificant, but as the universe expanded during inflation, they were stretched and amplified, becoming the seeds for all the structure we see today. These density variations were crucial for the formation of atoms. In the denser regions, gravity began to pull matter together, creating the first clumps of particles. Over time, these clumps grew larger, eventually forming the nuclei of hydrogen and helium atoms during Big Bang Nucleosynthesis. Without these initial fluctuations, matter might have been spread too evenly throughout the universe, making it impossible for atoms to form. What's truly remarkable is how these quantum fluctuations, born from the strange rules of quantum mechanics, set the stage for the entire cosmic story. They not only influenced the formation of atoms, but also laid the groundwork for galaxies, stars, and planets. In a way, the universe's largest structures owe their existence to the tiniest of beginnings. As we explore this theory, it's clear that quantum fluctuations were more than just random blips. They were the architects of the universe's first atoms. And with this understanding, we're ready to delve deeper into the cosmic mystery, uncovering how dark matter may have further shaped the early universe. Now shifting our gaze to the invisible yet omnipresent force that has shaped the cosmos in ways we are only beginning to understand, we delve into the mysterious influence of dark matter. While it remains unseen and elusive, dark matter's gravitational pull is believed to have been a key player in the formation of the universe's first atoms. Picture the early universe as a vast, chaotic expanse filled with particles and energy. Amidst this chaos, dark matter, which makes up about 27% of the universe's total mass and energy, began to exert its influence. Unlike ordinary matter, dark matter doesn't interact with light or other forms of electromagnetic radiation, but its gravitational effects are profound. These effects created subtle gravitational wells, areas where the pull of gravity was slightly stronger. These wells acted like cosmic traps, drawing in ordinary matter such as protons, neutrons, and electrons. Over time, the gravitational influence of dark matter helped gather these particles into denser regions, setting the stage for the formation of atomic nuclei. Without dark matter's gravitational scaffolding, ordinary matter might have remained too dispersed, making it difficult for atoms to coalesce. This process was especially crucial during the recombination era, when electrons combined with nuclei to form neutral hydrogen atoms. Dark matter's gravitational pull ensured that matter was concentrated enough for these interactions to occur efficiently. In essence, dark matter provided the cosmic framework that allowed the first atoms to take shape, paving the way for the formation of stars, galaxies, and ultimately, the universe as we know it. What's fascinating is that while dark matter remains invisible to us, its fingerprints are everywhere. From the large-scale structure of the universe to the formation of the first atoms, its influence is undeniable. As we continue to explore this enigmatic substance, we uncover more about how it shaped the early universe and set the stage for everything that followed. With this understanding of dark matter's role, we're ready to explore another pivotal moment in cosmic history, the cosmic microwave background and how it holds clues to the formation of the first atoms. Now stepping into the realm of cosmic echoes, we explore the cosmic microwave background, or CMB, a faint glow that permeates the universe and holds secrets about the formation of the first atoms. Imagine the universe just a few 100,000 years after the Big Bang as a hot, dense plasma of particles. Electrons, protons, and neutrons were constantly colliding, creating a foggy, opaque environment where light couldn't travel freely. But as the universe expanded and cooled, a monumental shift occurred. Around 380,000 years after the Big Bang, the temperature dropped enough for electrons to combine with protons and form neutral hydrogen atoms. This process, known as recombination, marked a turning point. For the first time, light could travel unimpeded through space, and the universe became transparent. The release of this light is what we now observe as the cosmic microwave background. It's like a snapshot of the universe at that precise moment, frozen in time and stretched by the expansion of the cosmos over billions of years. The CMB is not just a relic of the past, it's a treasure trove of information. By studying its subtle variations in temperature and density, scientists can piece together how matter was distributed in the early universe. These tiny fluctuations in the CMB reveal the seeds of structure that would later grow into galaxies and clusters of galaxies. They also provide clues about how the first atoms formed and how dark matter's gravitational influence shaped the distribution of matter. In essence, the CMB is a cosmic fingerprint, offering us a glimpse into the universe's infancy and the processes that gave rise to the first atoms. As we continue to analyze this ancient light, we uncover more about the universe's origins and the intricate dance of particles that set the stage for everything we see today. With the CMB as our guide, we're ready to delve deeper into the next chapter of cosmic history, the oscillations of the photon-baryon fluid and their role in shaping the early universe. Now shifting our gaze to the intricate dance of particles in the early universe, we encounter the photon-baryon fluid model. Picture the universe still in its infancy as a swirling sea of photons, particles of light, and baryons, which include protons and neutrons. Together, they formed a tightly coupled fluid where photons and baryons interacted so intensely that they moved as one. This photon-baryon fluid wasn't static, it was alive with oscillations like ripples spreading across the surface of a pond. These oscillations were driven by a tug-of-war between two forces, the pressure of photons pushing outward and the gravitational pull of matter pulling inward. As the universe expanded, these oscillations created patterns of compression and rarefaction, much like sound waves traveling through air. These ripples in the photon-baryon fluid had profound consequences. They left their mark on the cosmic microwave background, or CMB, imprinting it with subtle variations in temperature and density. These imprints are like cosmic fingerprints, revealing the conditions of the early universe and the processes that shaped it. The oscillations also played a crucial role in the formation of atoms. As the universe cooled, the photon-baryon fluid began to decouple, allowing protons and electrons to combine and form neutral hydrogen atoms. The patterns created by these oscillations influenced where matter clumped together, seeding the formation of the first structures in the universe, proto-galaxies and clusters that would eventually grow into the vast cosmic web we see today. By studying these oscillations and their imprints on the CMB, scientists can reconstruct the history of the early universe with remarkable precision. It's like listening to an ancient symphony where each note reveals a piece of the story of how the first atoms came to be. As we continue to unravel the mysteries of the photon-baryon fluid, we gain deeper insights into the forces that shape the cosmos. With this understanding, we're ready to explore the next chapter in our cosmic journey, the role of neutrinos in the early universe and how their decoupling influenced the formation of atoms. Now turning to the enigmatic world of neutrinos, we uncover another fascinating piece of the cosmic puzzle. Neutrinos, often called ghost particles, are incredibly lightweight and elusive, rarely interacting with other matter. Yet, in the early universe, they played a crucial role in shaping the conditions that allowed atoms to form. Just moments after the Big Bang, the universe was so hot and dense that neutrinos were tightly coupled with other particles, moving in lockstep with photons, electrons, and protons. But as the universe expanded and cooled, neutrinos began to decouple from matter. This decoupling happened when the universe was only about 1 second old, a blink of an eye in cosmic terms. Once decoupled, neutrinos streamed freely through space, barely interacting with anything else. But their departure wasn't without consequence. As they broke free, they carried away energy, subtly altering the balance of the universe. This energy loss affected the temperature and density of the remaining matter, creating ripples that would later influence how atoms formed. Neutrinos also played a key role in the universe's overall density. Because they are so abundant, billions of them pass through your body every second. Their collective mass, though tiny, contributed to the gravitational pull that shaped the early cosmos. This gravitational influence helped determine how matter clumped together, setting the stage for the formation of the first atomic structures. Interestingly, neutrinos may have left their own faint imprint on the cosmic microwave background, or CMB. While their effects are subtle compared to the Photon-baryon fluid, scientists believe that neutrinos could have slightly altered the distribution of matter, leaving behind clues about their role in the universe's infancy. By studying neutrinos and their decoupling, we gain a deeper understanding of how the universe transitioned from a hot, dense soup of particles to a cooler, more structured environment where atoms could form. These ghostly particles, though elusive, are a vital part of the story of our cosmic origins. With this insight into the role of neutrinos, we're ready to explore the next chapter in our journey. The recombination era, when electrons and protons finally combined to form the first neutral atoms, marking a pivotal moment in the universe's history. Now stepping into one of the most transformative moments in cosmic history, we arrive at the recombination era, a pivotal chapter that forever changed the universe. Imagine a time roughly 380,000 years after the Big Bang, when the cosmos was still a seething, opaque plasma of charged particles. Electrons and protons zipped around freely, constantly colliding with photons, making the universe a glowing, chaotic soup. But as the universe continued to expand and cool, something extraordinary happened. During this era, the temperature dropped to a point where electrons could finally slow down enough to be captured by protons. This process, known as recombination, led to the formation of the first neutral hydrogen atoms. For the first time, electrons and protons combined, creating stable, electrically neutral structures. This was a monumental shift as the universe transitioned from a hot, ionized plasma to a cooler, transparent gas. The implications of this transition were profound. Before recombination, photons, particles of light, were constantly scattered by free electrons, making the universe opaque. But once electrons were bound into atoms, photons could travel freely through space. This sudden release of light is what we now observe as the cosmic microwave background, or CMB, a faint glow that serves as a snapshot of the universe at this critical moment. The recombination era also set the stage for the next phase of cosmic evolution. With neutral atoms now dominating the scene, the universe became transparent, allowing light to travel vast distances. This transparency enabled the first structures, clouds of gas, to begin clumping together under the influence of gravity, eventually leading to the formation of stars and galaxies. In essence, the recombination era was the universe's first step toward structure and complexity. It marked the end of the cosmic dark ages and the dawn of a new era, where the building blocks of everything we see today began to take shape. As we continue our journey through the mysteries of the universe's first atoms, this era stands as a testament to the delicate balance of forces that shaped our cosmic home. With the universe now filled with neutral atoms, we're ready to explore how these early structures evolved, setting the stage for the next chapter in our cosmic story. Now shifting our focus to another fascinating piece of the cosmic puzzle, let's explore the role of primordial magnetic fields in shaping the universe's first atoms. While we often think of gravity as the dominant force in the early universe, magnetic fields may have played a subtle yet significant role in how matter came together. In the chaotic aftermath of the Big Bang, the universe was not only filled with particles and radiation, but also likely threaded with weak magnetic fields. These fields, though faint, could have influenced the movement of charged particles like electrons and protons. Imagine these magnetic fields as invisible threads weaving through the cosmic fabric, subtly guiding the flow of matter. One intriguing possibility is that these primordial magnetic fields helped create tiny variations in the density of matter. As particles moved under the influence of these fields, they may have clumped together in certain regions more than others. Over time, these slight differences in density could have grown, setting the stage for the formation of larger structures like galaxies and stars. But how did these magnetic fields originate in the first place? Some theories suggest they were generated during the universe's earliest moments, possibly during the inflationary period when space expanded rapidly. Others propose that they emerged later as turbulent motions in the hot plasma created electric currents, which in turn produced magnetic fields. While the exact origins remain a mystery, the effects of these fields could have been profound. By influencing the distribution of matter, they may have helped shape the cosmic web, the vast network of galaxies and voids that we see today. Even today, magnetic fields are found throughout the universe, from the spiral arms of galaxies to the jets of black holes, hinting at their enduring influence. As we continue to unravel the story of the universe's first atoms, the role of magnetic fields reminds us that even the smallest forces can have a lasting impact on the cosmos. With this in mind, we're ready to delve into the next chapter, where we'll explore another key piece of the cosmic puzzle, the baryon asymmetry problem. Now turning to one of the most puzzling mysteries of the cosmos, we encounter the baryon asymmetry problem. This is the question of why the universe is made almost entirely of matter, with very little antimatter to be found. If the Big Bang had created equal amounts of matter and antimatter, they should have annihilated each other, leaving behind a universe filled with nothing but energy. Yet here we are, surrounded by galaxies, stars, and planets all made of matter. So, what happened to the antimatter? To understand this, let's rewind to the earliest moments of the universe. In the extreme heat and density of the Big Bang, particles and antiparticles were constantly being created and destroyed. According to our current understanding of physics, matter and antimatter should have been produced in equal amounts. But something tipped the scales in favor of matter, allowing a tiny fraction of it to survive and form the building blocks of everything we see today. Scientists believe this imbalance might have been caused by a process called baryogenesis. This is a hypothetical event that occurred in the early universe, where certain conditions allowed matter to slightly outnumber antimatter. One possibility is that the laws of physics themselves are not perfectly symmetrical. For example, certain particle interactions might favor the creation of matter over antimatter, even if only by a tiny margin. Over time, this small difference could have grown, leading to the matter-dominated universe we observe today. The implications of this asymmetry are profound. Without it, the universe would have been a sea of radiation, with no atoms, no stars, and no planets. The fact that matter prevailed meant that protons and neutrons could combine to form atomic nuclei, which later captured electrons to create stable atoms. This was the foundation for all the structures we see in the cosmos, from the simplest hydrogen atoms to the complex molecules that make up life itself. As we continue to explore this mystery, experiments like those conducted at the Large Hadron Collider are searching for clues. By recreating the conditions of the early universe, scientists hope to uncover the mechanisms that led to this crucial imbalance. The baryon asymmetry problem not only deepens our understanding of the universe's origins, but also reminds us of how delicate and finely tuned the conditions for our existence truly are. With this in mind, we're ready to step into the next chapter, where we'll explore the Lepton epoch and its role in shaping the cosmos. Now shifting our focus to a pivotal moment in the universe's history, we arrive at the Lepton epoch. This era, which followed the Quark-Gluon Plasma phase, was a time when the universe was dominated by lightweight particles known as leptons. Among these were electrons, the familiar particles that orbit atomic nuclei, and neutrinos, elusive particles that barely interact with matter. Together, these leptons played a crucial role in shaping the cosmos as we know it. During the Lepton epoch, the universe was still incredibly hot and dense, but it had cooled enough for quarks to combine into protons and neutrons. However, the real stars of this era were the leptons. Electrons in particular were abundant, zipping through the primordial soup of particles. Neutrinos, on the other hand, were everywhere but interacted so weakly with other matter that they could travel vast distances without being disturbed. This made the universe a dynamic and energetic place, filled with constant particle interactions. One of the key events of this epoch was the decoupling of neutrinos. As the universe expanded and cooled, neutrinos stopped interacting with other particles and began to travel freely through space. This left behind a cosmic neutrino background, similar to the cosmic microwave background but much harder to detect. The decoupling of neutrinos marked a turning point, as it allowed the universe to transition into the next phase of its evolution. The Lepton epoch also set the stage for the formation of atoms. Electrons, which would later become essential components of atoms, were already present in large numbers. However, they couldn't yet combine with protons and neutrons to form stable atoms because the universe was still too hot. Instead, they existed in a plasma state, constantly colliding with photons and other particles. This chaotic environment was a necessary step in the universe's journey toward structure and complexity. As the Lepton epoch drew to a close, the universe continued to cool, paving the way for the next critical phase, the recombination era. It was during this time that electrons could finally combine with protons to form neutral hydrogen atoms, marking the birth of the first stable matter in the cosmos. Without the Lepton epoch, this crucial step in the universe's evolution might never have occurred. The Lepton epoch reminds us of the intricate and interconnected processes that shaped the early universe. From the dominance of leptons to the decoupling of neutrinos, each event played a vital role in creating the conditions necessary for atoms and ultimately life to emerge. As we move forward, we'll explore how these early stages culminated in the formation of the first atoms, bringing us one step closer to understanding the origins of everything around us. Now stepping into the next chapter of the universe's story, we arrive at the hadron epoch. This was a time when the building blocks of matter as we know it began to take shape. Following the Lepton epoch, the universe had cooled further, allowing quarks, those fundamental particles we discussed earlier, to come together and form protons and neutrons. These particles, collectively known as hadrons, would become the foundation of atomic nuclei, setting the stage for the creation of the first atoms. During the hadron epoch, the universe was still incredibly energetic, but the temperature had dropped enough for quarks to bind together through the strong nuclear force. This force, one of the four fundamental forces of nature, is what holds quarks together to form protons and neutrons. Without it, matter as we know it simply wouldn't exist. Imagine the universe at this time as a vast, chaotic workshop where quarks were constantly combining and recombining, eventually settling into the stable forms of protons and neutrons. This period was crucial because it marked the first time that the basic ingredients for atomic nuclei were present. Protons and neutrons are the core components of atomic nuclei, and their formation was a necessary step toward the creation of atoms. However, it's important to note that during the hadron epoch, these particles were still too energetic to combine into stable nuclei. The universe was still too hot, and the constant collisions between particles kept them from settling down. One fascinating aspect of the hadron epoch is the delicate balance that allowed protons and neutrons to form. If the universe had been even slightly hotter, quarks might not have been able to bind together. On the other hand, if it had been cooler, the process might have happened too quickly, potentially altering the composition of matter. This fine-tuning highlights just how precise the conditions of the early universe needed to be for the formation of matter as we know it. As the hadron epoch progressed, the universe continued to expand and cool, eventually reaching a point where protons and neutrons could begin to combine into atomic nuclei. This would set the stage for the next critical phase, nucleosynthesis, where the first elements like hydrogen and helium began to form. Without the hadron epoch, the universe would have lacked the essential building blocks needed for atoms, stars, and galaxies to emerge. The hadron epoch serves as a reminder of the intricate processes that shaped the early universe. From the binding of quarks to the formation of protons and neutrons, each step was essential in creating the conditions necessary for the cosmos to evolve. As we move forward, we'll explore how these early particles came together to form the first atomic nuclei, bringing us closer to understanding the origins of the universe's first atoms. Now shifting our gaze to another intriguing piece of the cosmic puzzle, we arrive at the role of cosmic strings. These hypothetical, thread-like structures are thought to have formed in the early universe, potentially playing a significant role in shaping the distribution of matter. Imagine them as incredibly thin, yet immensely dense filaments stretching across the cosmos, remnants of the universe's earliest moments. While cosmic strings remain theoretical, their existence could help explain some of the irregularities we observe in the distribution of galaxies and other large-scale structures. Cosmic strings are believed to have formed during a phase transition in the early universe, much like cracks forming in ice as water freezes. These transitions occurred as the universe cooled, and different regions of space underwent changes in their fundamental properties. The result was the creation of these one-dimensional defects cosmic strings that carried immense amounts of energy. Despite being incredibly thin, their gravitational influence could have been profound, potentially acting as gravitational lenses or even creating density variations in the surrounding matter. One of the most fascinating aspects of cosmic strings is their potential impact on the formation of atoms. If these strings existed, their gravitational pull could have caused matter to clump together in specific regions, creating the seeds for future galaxies and star systems. This clustering of matter would have been essential for the formation of atomic nuclei, as it provided the necessary density for particles to collide and combine. In this way, cosmic strings might have indirectly influenced the creation of the first atoms, setting the stage for the universe's evolution. However, it's important to note that cosmic strings remain a speculative concept. While they offer a compelling explanation for certain cosmic phenomena, their existence has yet to be confirmed through direct observation. Scientists continue to search for evidence, such as gravitational waves or distortions in the cosmic microwave background, that could point to their presence. Until then, cosmic strings remain a tantalizing possibility, one that adds another layer of mystery to our understanding of the early universe. As we explore the role of cosmic strings, we're reminded of how much remains unknown about the universe's earliest moments. These theoretical structures, if they exist, could hold the key to understanding not only the distribution of matter, but also the intricate processes that led to the formation of atoms. With this in mind, we turn our attention to the next theory, where we'll delve into the Multiverse hypothesis and its implications for the origins of the first atoms. Now turning to a concept that stretches the boundaries of our imagination, we arrive at the Multiverse hypothesis. This theory suggests that our universe is just one of countless others, each with its own unique set of physical laws and constants. Picture a vast cosmic tapestry where every thread represents a different universe, each woven with its own rules of physics. In some of these universes, the conditions might be so different that atoms as we know them could never form, while in others, the process of atom formation might unfold in ways we can scarcely comprehend. The multiverse hypothesis raises fascinating questions about the origins of the first atoms. If other universes exist, their physical constants, such as the strength of gravity or the charge of an electron, could vary dramatically from ours. These differences would profoundly influence how atoms form and behave. For instance, in a universe where the electromagnetic force is weaker, atoms might struggle to hold together, making stable matter impossible. Conversely, in a universe with stronger nuclear forces, atoms could form more readily, leading to a cosmos teeming with complex structures. One of the most intriguing aspects of this theory is its potential to explain why our universe seems so finely tuned for the existence of atoms and, by extension, life. If there are countless universes, each with different physical constants, it's possible that only a small fraction of them have the right conditions for atoms to form. In this view, our universe might simply be one of the rare ones where everything aligned just right, allowing atoms to emerge and set the stage for everything we see today. However, it's important to emphasize that the multiverse hypothesis remains highly speculative. While it offers a compelling framework for understanding the fine-tuning of our universe, there is currently no direct evidence to support the existence of other universes. Scientists continue to explore this idea through mathematical models and theoretical physics, but for now, it remains a tantalizing possibility rather than a proven fact. Despite its speculative nature, the multiverse hypothesis invites us to think beyond the confines of our own universe and consider the vast array of possibilities that might exist. It challenges us to imagine a cosmos far more complex and diverse than we've ever imagined, where the formation of atoms, and perhaps even life, might follow entirely different rules. With this in mind, we now shift our focus to the anthropic principle, a theory that explores the idea that the conditions for atom formation were fine-tuned to allow life to exist. Now shifting our gaze to a theory that bridges the realms of science and philosophy, we encounter the anthropic principle. This idea suggests that the conditions in our universe, specifically those that allowed the formation of atoms, were finely tuned to make life possible. It's as if the universe itself had a blueprint designed to create the perfect environment for atoms to exist and ultimately for life to emerge. At its core, the anthropic principle raises a profound question. Why does our universe have the precise set of physical constants and laws that allow atoms to form and sustain life? For example, if the strength of gravity were even slightly different, or if the charge of an electron were altered, atoms might never have come together in the stable structures we see today. This fine-tuning has led some to argue that our universe is uniquely suited for life, almost as if it were tailored for that purpose. From a scientific perspective, the anthropic principle offers a way to interpret the apparent fine-tuning of the universe. It doesn't necessarily explain why these conditions exist, but it provides a framework for understanding their significance. Some scientists suggest that this fine-tuning could be a result of chance, a lucky roll of the cosmic dice. Others propose that it might point to deeper laws of physics that we have yet to uncover, or even to the existence of multiple universes, each with its own set of physical constants. Philosophically, the anthropic principle invites us to reflect on our place in the cosmos. If the conditions for life are so rare and specific, what does that mean for our existence? Some see it as evidence of a purposeful design, while others view it as a reminder of the extraordinary improbability of life in an otherwise vast and indifferent universe. This duality makes the anthropic principle a fascinating topic, blending hard science with deep existential questions. However, it's important to note that the anthropic principle is not without its critics. Some argue that it's a tautology, a statement that seems profound but ultimately says little. After all, if the universe weren't fine-tuned for life, we wouldn't be here to observe it. Others caution against using the principle to draw conclusions about the nature of reality, as it doesn't provide concrete answers about why the universe is the way it is. Despite these debates, the anthropic principle remains a compelling lens through which to view the origins of atoms and the emergence of life. It challenges us to consider the delicate balance of forces that make our existence possible and to ponder the deeper mysteries of the cosmos. With this in mind, we now turn our attention to the role of supersymmetry, a theory that seeks to unify the fundamental forces and particles of the universe, offering new insights into the formation of the first atoms. Now stepping into the realm of theoretical physics, we encounter supersymmetry, a groundbreaking idea that could reshape our understanding of the universe's earliest moments. Supersymmetry, often abbreviated as SUSY, proposes a profound connection between the two fundamental classes of particles, fermions, which make up matter, and bosons, which carry forces. This theory suggests that every known particle has a yet-to-be-discovered superpartner, a mirror image with different properties. For example, an electron, a fermion, would have a bosonic counterpart called a selectron, while a photon, a boson, would pair with a fermionic photino. So, how does this relate to the formation of the first atoms? Supersymmetry offers a potential explanation for the delicate balance of forces and particles in the early universe. During the chaotic moments following the Big Bang, the universe was a seething cauldron of energy and particles. Supersymmetry posits that the interactions between these superpartners could have stabilized the conditions necessary for atoms to form. For instance, the extra particles predicted by SUSY might have influenced the rate at which protons and neutrons combined, ensuring the right mix of elements emerged. One of the most exciting aspects of supersymmetry is its potential to unify the fundamental forces of nature. Currently, physicists describe the universe using four forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. While the standard model of particle physics explains three of these forces, gravity remains stubbornly separate. Supersymmetry offers a framework where these forces could merge into a single, unified description at extremely high energies, like those present in the early universe. This unification could provide clues about how the first atoms came into existence, as it would reveal the underlying symmetry that governed the cosmos at its birth. However, supersymmetry is not without its challenges. Despite decades of searching, no direct evidence of superpartners has been found. Experiments at the Large Hadron Collider and other facilities have yet to detect these elusive particles, leaving some to question whether SUSY is a dead end. Yet, many physicists remain optimistic, arguing that the energy scales required to observe superpartners might simply be beyond our current technological reach. The search continues, driven by the tantalizing possibility that supersymmetry could unlock some of the universe's deepest secrets. As we explore supersymmetry, it's worth considering its broader implications. If proven true, SUSY could not only explain the formation of the first atoms, but also shed light on the nature of dark matter, the mysterious substance that makes up most of the universe's mass. Some theories suggest that the lightest superpartner could be a candidate for dark matter, providing a potential link between the visible and invisible cosmos. In the grand tapestry of cosmic theories, supersymmetry stands out as a bold and elegant idea, one that bridges the gap between the known and the unknown. While its full implications remain to be seen, it offers a compelling vision of a universe governed by symmetry and unity, where the first atoms emerged from a dance of particles and forces we are only beginning to understand. With this in mind, we now turn our attention to the holographic principle, a theory that challenges our very understanding of space, time, and the fabric of reality. Now shifting our perspective to a truly mind-bending idea, let's dive into the holographic principle. This theory proposes something extraordinary, that all the information in our three-dimensional universe might actually be encoded on a two-dimensional boundary like a cosmic projection. Imagine the universe as a hologram where every detail we see, stars, galaxies, even atoms, is a kind of shadow cast from a lower dimensional surface. It's a concept that challenges our very understanding of space, time, and reality itself. But how does this relate to the formation of the first atoms? The holographic principle suggests that the fundamental building blocks of the universe, including atoms, might emerge from the interactions of information encoded on this boundary. In the early universe, as particles and forces began to take shape, this principle could imply that the properties of atoms, their mass, charge, and structure were determined by the way information was processed and projected from this lower dimensional surface. It's a speculative idea, but one that offers a radical new way to think about how the universe's first structures came into being. One of the most intriguing aspects of the holographic principle is its connection to black holes. Physicists have discovered that the amount of information a black hole can contain is proportional to its surface area, not its volume. This observation aligns with the holographic principle, suggesting that the universe might operate in a similar way. If true, this could mean that the formation of atoms, and by extension all matter, is deeply tied to the way information is stored and processed on cosmic scales. Of course, the holographic principle is still highly speculative, and much of it remains theoretical. There's no direct experimental evidence to confirm it, and the mathematics behind it is incredibly complex. Yet, it's a theory that captures the imagination, offering a glimpse into a universe where the very fabric of reality might be far stranger than we've ever imagined. It challenges us to rethink not just how atoms formed, but what the universe truly is at its most fundamental level. As we ponder the holographic principle, it's worth considering its broader implications. If the universe is indeed a hologram, then the formation of atoms might be just one small part of a much larger, interconnected system. It's a theory that blurs the line between physics and philosophy, inviting us to explore the deepest mysteries of existence. And with that, we move forward to the Ekpyrotic universe theory, which offers yet another fascinating perspective on the origins of the cosmos. Now shifting our focus to another groundbreaking idea, let's explore the Ekpyrotic universe theory. This model proposes that our universe was born not from a single explosive event, but from the collision of two higher dimensional objects known as branes. Picture these branes as vast, flat sheets existing in a higher dimensional space, moving toward each other until they collide. This collision, according to the theory, released an enormous amount of energy, setting the stage for the creation of our universe as we know it. But how does this relate to the formation of the first atoms? In the Ekpyrotic model, the collision of branes would have generated intense heat and energy, creating a hot, dense environment similar to the conditions described in the Big Bang Theory. As the universe expanded and cooled, particles like quarks and electrons began to form, eventually combining to create protons, neutrons, and ultimately the first atoms. This process mirrors the steps of Big Bang Nucleosynthesis, but with a unique twist. The initial conditions were shaped by the collision of branes rather than a singular explosion. One of the most fascinating aspects of the Ekpyrotic model is its ability to address some of the challenges faced by the Big Bang Theory. For instance, it provides a potential explanation for the uniformity of the cosmic microwave background radiation, as the collision of branes could have smoothed out irregularities in the early universe. This smoothing effect might have created the ideal conditions for atoms to form in a more uniform and predictable manner. However, like many theories about the early universe, the Ekpyrotic model is still speculative. While it offers a compelling alternative to the Big Bang, it relies on the existence of higher dimensional branes which have yet to be observed or confirmed. The mathematics behind the theory is also highly complex, making it difficult to test experimentally. Despite these challenges, the Ekpyrotic universe theory remains an intriguing possibility, inviting us to consider a cosmos shaped by forces beyond our three-dimensional experience. As we reflect on the Ekpyrotic model, it's worth noting how it expands our understanding of the universe's origins. By suggesting that atoms formed in the aftermath of a brane collision, this theory opens up new avenues for exploring the fundamental nature of reality. It challenges us to think beyond the confines of traditional cosmology and consider the possibility that our universe is just one piece of a much larger, multidimensional puzzle. And with that, we turn our attention to the cyclic universe model, which offers yet another captivating perspective on the cosmos and its beginnings. Now turning to the cyclic universe model, we encounter a theory that paints the cosmos as an eternal dance of expansion and contraction. Unlike the Big Bang theory, which suggests a singular beginning, the cyclic model proposes that our universe has no true starting point. Instead, it undergoes endless cycles, each beginning with a Big Bang-like event and ending in a big crunch, only to start anew. This idea challenges our understanding of time and space, suggesting that the universe is not a one-time creation but a recurring phenomenon. So, how does this relate to the formation of the first atoms? In each cycle, as the universe expands, it cools, allowing particles to form and combine into atoms, much like in the Big Bang nucleosynthesis process. However, as the cycle progresses and the universe begins to contract, these atoms are torn apart, returning to their most basic components. When the next cycle begins, the process repeats, with atoms forming once again under similar conditions. This cyclical nature implies that the formation of atoms is not a unique event but a recurring feature of the universe's endless rhythm. One of the most intriguing aspects of the cyclic model is its potential to explain the fine-tuning of the universe. If each cycle resets the conditions for atom formation, it could provide a natural explanation for why the fundamental constants and laws of physics seem so perfectly suited for the existence of atoms and, by extension, life. This idea offers a fascinating alternative to the anthropic principle, suggesting that the universe's conditions are not fine-tuned by chance, but are the result of an infinite series of trials and errors across countless cycles. However, the cyclic universe model is not without its challenges. For one, it requires a mechanism to prevent the universe from collapsing into a singularity during the Big Crunch, which remains a topic of intense debate among physicists. Additionally, the model relies on speculative concepts like dark energy and higher dimensional physics, which are still not fully understood. Despite these uncertainties, the cyclic model continues to captivate scientists and enthusiasts alike, offering a bold and imaginative perspective on the cosmos. As we consider the implications of the cyclic universe theory, we're reminded of the vastness and complexity of the universe's story. By suggesting that atom formation is a recurring event, this model invites us to rethink our place in the cosmos. It challenges us to imagine a universe that is not only vast in space but also infinite in time, where the first atoms we study today may have formed countless times before and will form countless times again. With this thought-provoking idea in mind, we now turn our attention to the role of primordial black holes in shaping the early universe. Now shifting our focus to the role of primordial black holes, we delve into a theory that suggests these mysterious objects may have played a crucial part in shaping the early universe. Unlike the black holes we know today, which form from the collapse of massive stars, primordial black holes are thought to have emerged in the first moments after the Big Bang. These tiny, dense objects could have formed from the extreme density fluctuations present in the early universe, acting as seeds around which matter began to gather. So, how might these primordial black holes have influenced the formation of atoms? One possibility is that their immense gravitational pull could have attracted nearby particles, creating regions of higher density. These dense pockets of matter would have provided the perfect conditions for atoms to form, as particles were brought closer together, increasing the likelihood of collisions and interactions. In this way, primordial black holes might have acted as cosmic catalysts, accelerating the process of atom formation in the early universe. Another intriguing aspect of this theory is the potential connection between primordial black holes and dark matter. Some scientists propose that these ancient black holes could account for a portion of the universe's dark matter, which we know exerts a gravitational influence but remains invisible to us. If true, this would mean that primordial black holes not only helped shape the distribution of matter, but also played a role in the universe's overall structure, influencing the formation of galaxies and larger cosmic structures. However, the idea of primordial black holes is not without its challenges. Detecting these objects is incredibly difficult, as they are thought to be much smaller than stellar black holes and could have evaporated over time due to a process known as Hawking radiation. Additionally, their existence remains speculative, as no direct evidence has been found to confirm their presence in the early universe. Despite these uncertainties, the theory continues to spark interest, offering a unique perspective on how the cosmos might have taken shape. As we explore the potential influence of primordial black holes, we're reminded of the many unanswered questions that still surround the early universe. These enigmatic objects, if they exist, could hold the key to understanding not only the formation of atoms, but also the larger mysteries of dark matter and cosmic structure. With this thought in mind, we now turn our attention to the Axion hypothesis, another fascinating idea that seeks to explain the universe's earliest moments. Now shifting our gaze to another intriguing piece of the cosmic puzzle, we arrive at the Axion hypothesis. This theory introduces us to axions, hypothetical particles that have captured the imagination of physicists for decades. Unlike the particles we're familiar with, axions are incredibly light and interact so weakly with ordinary matter that they've remained undetected so far. But why are they so important? Well, axions are one of the leading candidates for explaining dark matter, that mysterious substance that makes up a significant portion of the universe's mass but remains invisible to us. So, how might axions have influenced the formation of the first atoms? To understand this, we need to look back at the early universe, a time when particles were zipping around in a hot, dense soup. Axions, if they exist, would have been among these particles, moving through the chaos without interacting much with anything else. But their presence could have had a subtle yet profound effect. As the universe expanded and cooled, axions might have helped stabilize the density of matter, creating the right conditions for atoms to form. Their gravitational influence, though weak, could have nudged particles into the right places, allowing hydrogen and helium nuclei to come together and capture electrons, forming the first neutral atoms. What makes axions particularly fascinating is their dual role. Not only could they explain dark matter, but they might also solve another mystery in physics, the strong charge parity problem. This is a long-standing question about why certain interactions in the universe don't behave the way we'd expect them to. Axions, with their unique properties, could provide an elegant solution to both problems, tying together two of the biggest puzzles in modern physics. Of course, the Axion hypothesis is still just that, a hypothesis. Detecting these elusive particles is no easy task, and experiments are ongoing to find evidence of their existence. If axions are discovered, it would be a monumental breakthrough, shedding light not only on dark matter but also on the very fabric of the early universe. Their discovery could help us understand how the first atoms came to be and how the universe evolved into the complex, structured cosmos we see today. As we ponder the potential role of axions, we're reminded once again of the intricate dance of particles and forces that shape the universe. These tiny, hypothetical particles might hold the key to unlocking some of the deepest mysteries of the cosmos. With this in mind, we now turn our attention to the string theory connection, another fascinating idea that seeks to bridge the gap between the smallest particles and the largest structures in the universe. Now, as we venture into the realm of the unimaginably small, we encounter the string theory connection, a theory that reimagines the very fabric of reality. String theory proposes that the fundamental building blocks of the universe are not point-like particles, as we've long believed, but tiny, vibrating strings. These strings, each vibrating at different frequencies, give rise to the particles we observe, from electrons to quarks. But how does this relate to the formation of the first atoms? Let's unravel this cosmic thread. In the early universe, as particles collided and combined, the behavior of these strings would have played a crucial role. String theory suggests that the vibrations of these strings determine the properties of particles, such as their mass and charge. This means that the specific ways these strings vibrated could have influenced how protons, neutrons, and electrons formed and interacted. For instance, the stability of hydrogen and helium atoms. The first atoms to emerge might have been shaped by the precise vibrational patterns of these strings. One of the most intriguing aspects of string theory is its potential to unify the fundamental forces of nature. In the early universe, gravity, electromagnetism, and the nuclear forces were all intertwined. String theory offers a framework where these forces emerge from the interactions of strings, providing a unified description of the cosmos. This unification could explain how the conditions for atom formation were set in motion, as the forces governing particle interactions were finely tuned by the underlying string dynamics. However, string theory is not without its challenges. It operates in higher dimensions, often 10 or 11, far beyond the 3 spatial dimensions we experience. While this might seem abstract, these extra dimensions could have played a hidden role in the early universe, influencing how particles behaved and how atoms came together. For example, the compactification of these extra dimensions, essentially how they fold in on themselves, might have determined the strength of the forces that allowed atoms to form. Despite its complexity, string theory offers a tantalizing glimpse into the origins of the universe's first atoms. By reimagining particles as vibrating strings, it provides a new perspective on how the fundamental building blocks of matter emerged. While much of string theory remains speculative, its implications for understanding the early universe are profound. If proven, it could revolutionize our understanding of not just atoms, but the very nature of reality itself. With this in mind, we now turn to the role of quantum gravity, another groundbreaking idea that seeks to bridge the gap between the smallest particles and the largest structures in the cosmos. Now, as we step into the realm of quantum gravity, we find ourselves at the crossroads of 2 of the most profound theories in physics: quantum mechanics and general relativity. Quantum gravity seeks to bridge the gap between the microscopic world of particles and the vast cosmic scales governed by gravity. But what does this mean for the formation of the universe's first atoms? Let's explore this fascinating connection. In the early universe, the conditions were so extreme that the effects of quantum mechanics and gravity were deeply intertwined. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the force of gravity that shapes the cosmos. However, these 2 theories don't naturally align. Quantum mechanics deals with probabilities and uncertainties, while general relativity is deterministic, describing gravity as the curvature of spacetime. Quantum gravity aims to unify these seemingly incompatible frameworks, offering a deeper understanding of how the universe operated in its earliest moments. One of the key ideas in quantum gravity is that spacetime itself might be quantized, meaning it's made up of tiny, discrete units rather than being smooth and continuous. Imagine spacetime as a fabric woven from countless threads, each representing a quantum of space and time. In the early universe, these quantum threads would have been highly dynamic, fluctuating wildly as the cosmos expanded and cooled. These fluctuations could have influenced how particles interacted, potentially shaping the formation of the first atoms. For instance, during the epoch of nucleosynthesis, when protons and neutrons combined to form atomic nuclei, quantum gravitational effects might have played a subtle but crucial role. The tiny ripples in spacetime could have affected the energy levels of particles, altering the rates at which they combined. This, in turn, could have influenced the abundance of hydrogen and helium, the first elements to emerge. While these effects would have been incredibly small, they might have left an imprint on the universe's early structure. Another intriguing possibility is that quantum gravity could explain the initial conditions of the Big Bang itself. Some theories suggest that the Big Bang was not a singular event but rather a transition from a previous state of the universe, governed by quantum gravitational laws. If true, this would mean that the formation of atoms was not just a consequence of the Big Bang, but also a result of the quantum gravitational processes that preceded it. This idea opens up a whole new perspective on how the universe's first building blocks came into existence. However, quantum gravity remains one of the most challenging areas of theoretical physics. Unlike string theory, which proposes a specific framework, quantum gravity encompasses a variety of approaches, such as loop quantum gravity and causal dynamical triangulations. Each of these offers unique insights but also raises new questions. For example, how do quantum gravitational effects manifest at the scales relevant to atom formation? And how can we test these ideas experimentally, given the extreme energies involved? Despite these challenges, the pursuit of quantum gravity holds immense promise. By unifying quantum mechanics and general relativity, it could provide a complete picture of the early universe, shedding light on how the first atoms formed and how the cosmos evolved into the complex structure we see today. As we continue to explore this frontier, we inch closer to understanding not just the origins of atoms, but the very fabric of reality itself. With this in mind, we now turn to the plasma universe theory, which offers a different perspective on how electromagnetic forces shaped the early cosmos. Now shifting our focus to the plasma universe theory, we enter a realm where electromagnetic forces take center stage in shaping the cosmos. Unlike the gravitational dominance we often associate with the universe's evolution, this theory proposes that electromagnetic interactions were the primary drivers in the early universe, influencing the formation of atoms in profound ways. In the plasma universe model, the early cosmos was not just a hot, dense soup of particles, but a sea of ionized gas plasma, where charged particles like electrons and protons moved freely under the influence of electromagnetic fields. This plasma was highly conductive, meaning it could carry electric currents and generate magnetic fields on vast scales. These electromagnetic forces, far stronger than gravity at such small scales, could have orchestrated the behavior of particles in ways that gravity alone could not. One of the key ideas here is that electromagnetic interactions might have played a crucial role in the formation of the first atoms. As the universe expanded and cooled, electrons and protons began to combine to form neutral hydrogen atoms during the recombination era. But in the plasma universe model, this process wasn't just a simple matter of particles coming together due to cooling. Instead, electromagnetic forces could have guided the movement of charged particles, creating regions of higher density where atoms were more likely to form. This could explain why the universe's matter isn't uniformly distributed, but instead clumped into galaxies, stars, and other structures. Another fascinating aspect of this theory is the idea that cosmic magnetic fields, generated by the motion of charged particles in the plasma, could have influenced the formation of atoms. These magnetic fields might have acted like cosmic scaffolding, shaping the distribution of matter and energy in the early universe. Over time, these fields could have amplified tiny fluctuations in the plasma, leading to the large-scale structures we observe today. This process, known as magnetogenesis, offers a compelling alternative to the purely gravitational explanations often associated with structure formation. The plasma universe theory also challenges some of the assumptions of the Big Bang model. For instance, it suggests that electromagnetic forces could have played a role in the initial expansion of the universe, rather than relying solely on the inflationary mechanism. This opens up new possibilities for understanding the universe's origins, as well as the conditions that allowed atoms to form. However, like many theories about the early universe, the plasma universe model is not without its challenges. One of the main criticisms is that it requires a significant departure from the standard cosmological model, which has been supported by a wealth of observational evidence, such as the cosmic microwave background. Proponents of the plasma universe theory argue that these observations can be reinterpreted within their framework, but this remains a topic of debate among scientists. Despite these debates, the plasma universe theory offers a unique perspective on the formation of atoms and the evolution of the cosmos. By emphasizing the role of electromagnetic forces, it invites us to reconsider the fundamental processes that shaped the universe in its infancy. As we continue to explore this intriguing idea, we gain new insights into the complex interplay of forces that gave rise to the first atoms, and ultimately to everything we see around us today. With this in mind, we now turn our attention to the role of neutron stars, which may have contributed to the formation of heavier atoms in the universe. Now shifting our gaze to the remnants of stellar explosions, we explore the role of neutron stars in the cosmic story of atom formation. These incredibly dense objects, born from the violent deaths of massive stars, are not just fascinating in their own right. They may have played a pivotal role in creating the heavier elements that make up our universe today. When a massive star exhausts its nuclear fuel, it undergoes a catastrophic explosion known as a supernova. This explosion scatters the star's outer layers into space, leaving behind a dense core, a neutron star. These cores are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth. But beyond their sheer density, neutron stars are also cosmic forges, capable of producing elements far heavier than those formed during the Big Bang or in the cores of ordinary stars. The process by which neutron stars contribute to the formation of heavier atoms is called nucleosynthesis. During a supernova, the intense heat and pressure can fuse lighter elements into heavier ones, such as gold, platinum, and uranium. But neutron stars take this process even further. When two neutron stars collide, a rare and spectacular event, they release an enormous amount of energy and create conditions extreme enough to produce some of the heaviest elements in the periodic table. This process, known as rapid neutron capture or the R process, is thought to be responsible for the creation of many of the rare elements we find on Earth and throughout the cosmos. The significance of neutron stars in the formation of heavier atoms becomes even clearer when we consider the distribution of these elements in the universe. Observations of ancient stars and distant galaxies reveal traces of heavy elements that could only have been produced through processes like the R process. This suggests that neutron star collisions, though rare, have been a crucial source of these materials since the early days of the universe. But neutron stars don't just create heavy elements, they also distribute them. The material ejected during a neutron star collision is flung into space at incredible speeds, eventually mixing with interstellar gas and dust. Over time, this enriched material becomes part of new stars, planets, and even life itself. In this way, neutron stars are not just remnants of stellar death, they are also seeds of cosmic rebirth, contributing to the ongoing cycle of creation in the universe. While the role of neutron stars in nucleosynthesis is widely accepted, there are still many questions to explore. For instance, how often do neutron star collisions occur, and how much material do they produce? How do these events influence the chemical evolution of galaxies? And could there be other, yet undiscovered processes that contribute to the formation of heavy elements? These questions remind us that the story of the universe's atoms is still being written, with neutron stars playing a starring role. As we continue to unravel the mysteries of neutron stars and their contributions to the cosmos, we gain a deeper appreciation for the intricate processes that shape the universe. From the explosive birth of these stellar remnants to their role in creating the building blocks of planets and life, neutron stars remind us that even in the aftermath of destruction, creation is always possible. With this in mind, we now turn our attention to the Panspermia connection, exploring the idea that atoms essential for life might have been distributed across the universe by comets or meteorites. Now shifting our focus to a theory that bridges the cosmos and the origins of life itself, we delve into the Panspermia connection. This intriguing idea suggests that the atoms essential for life might not have originated solely on Earth, but could have been carried across the universe by comets, meteorites, or even interstellar dust. While this concept may sound like science fiction, it raises fascinating questions about how life's building blocks could have traveled vast distances to reach our planet. The Panspermia hypothesis proposes that organic molecules, or even simple life forms, could survive the harsh conditions of space and hitch a ride on celestial objects. Comets and meteorites, for instance, are known to contain water, amino acids, and other compounds that are crucial for life as we know it. When these objects collide with planets, they could deliver these materials, seeding the potential for life to emerge. This idea gains traction when we consider that some of the oldest meteorites found on Earth contain organic molecules, suggesting that such materials have been arriving here for billions of years. But how plausible is this theory? While it's true that comets and meteorites carry organic compounds, the journey through space is far from hospitable. Radiation, extreme temperatures, and the vacuum of space pose significant challenges to the survival of complex molecules, let alone living organisms. However, some experiments have shown that certain microbes can withstand these conditions, at least for a limited time. This has led scientists to speculate that life's ingredients, or perhaps even life itself, could have been transported across the cosmos. The Panspermia connection also ties into the broader question of how life began on Earth. If the atoms and molecules necessary for life were delivered from elsewhere, it could mean that the origins of life are not unique to our planet. This idea opens up the possibility that life might exist elsewhere in the universe, carried by similar processes to other habitable worlds. It's a thought that both excites and challenges our understanding of life's beginnings. Despite its speculative nature, the Panspermia hypothesis offers a compelling perspective on the interconnectedness of the universe. It suggests that the atoms that make up our bodies, our planet, and even the stars above might have traveled unimaginable distances to bring us to where we are today. While the theory remains unproven, it serves as a reminder of the vast and mysterious processes that shape our existence. As we ponder the Panspermia connection, we're reminded that the story of the universe's atoms is not just about their creation, but also their journey. From the hearts of stars to the depths of space, these atoms have traversed the cosmos, carrying with them the potential for life and the mysteries of our origins. With this in mind, we now turn our attention to the role of cosmic rays, exploring how these high-energy particles might have influenced the formation of atoms in the early universe. Now shifting our gaze to the skies, we explore the role of cosmic rays in shaping the universe's earliest atoms. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, originating from powerful cosmic events like supernova, black holes, and even distant galaxies. These particles, though invisible to the naked eye, may have played a surprising role in the formation of atoms during the universe's infancy. In the early universe, the environment was a chaotic mix of energy and matter, with particles constantly colliding and interacting. Cosmic rays, with their immense energy, could have influenced these interactions in significant ways. For instance, when cosmic rays collide with atomic nuclei, they can break them apart, creating smaller particles or even triggering the formation of new atoms. This process, known as spallation, might have contributed to the creation of lighter elements like lithium, beryllium, and boron, which are less abundant than hydrogen and helium but still crucial for the universe's chemical diversity. But cosmic rays didn't just break things apart, they also helped build. The energy from these particles could have provided the necessary push for certain nuclear reactions to occur, enabling the formation of more complex atomic structures. In this way, cosmic rays might have acted as cosmic catalysts, speeding up processes that would have otherwise taken much longer to unfold. Another intriguing possibility is that cosmic rays influenced the distribution of matter in the early universe. Their high energy could have caused fluctuations in the density of particles, creating pockets where atoms were more likely to form. These density variations might have laid the groundwork for the large-scale structures we see today, such as galaxies and galaxy clusters. While the exact role of cosmic rays in atom formation remains a topic of ongoing research, their presence in the early universe is undeniable. These particles serve as a reminder of the dynamic and interconnected nature of cosmic processes. From the smallest atoms to the largest structures, cosmic rays may have left their mark on the fabric of the universe. As we consider the influence of cosmic rays, we're reminded that the story of the universe's atoms is not just about their creation, but also the forces that shaped them. From the explosive power of supernova to the subtle interactions of high-energy particles, every process played a part in bringing the cosmos to life. With this in mind, we now turn to the final theory in our exploration, the simulation hypothesis, a controversial idea that challenges our very understanding of reality. Now, as we step into the final chapter of our cosmic journey, we encounter a theory that challenges the very foundation of our understanding, the simulation hypothesis. This provocative idea suggests that our universe, with all its complexity and wonder, might not be the ultimate reality, but rather an incredibly advanced simulation created by an unknown intelligence. Imagine for a moment that everything we perceive, the stars, the galaxies, and even the atoms that make up our world, could be part of a vast, intricate program running on some unimaginable cosmic computer. At its core, the simulation hypothesis raises profound questions about the nature of reality. If our universe is a simulation, then the laws of physics, the constants that govern the behavior of matter and energy, and even the formation of atoms could be the result of carefully designed code. This would mean that the first atoms, the building blocks of everything we see, were not born out of natural processes but were instead programmed into existence. It's a mind-bending thought, but one that has gained traction among some scientists and philosophers. One of the key arguments supporting this theory is the precision of the universe's physical constants. For example, the fine structure constant, which governs the strength of electromagnetic interactions, is so finely tuned that even a slight change would make the formation of atoms impossible. Proponents of the simulation hypothesis argue that such precision is more likely the result of deliberate design than random chance. In this view, the first atoms were not the product of cosmic accidents, but the outcome of a meticulously crafted simulation. Another intriguing aspect of this theory is how it might explain the strange behavior of particles at the quantum level. Quantum mechanics, with its probabilities and uncertainties, has long puzzled scientists. But if our universe is a simulation, these oddities could be the result of computational limitations or shortcuts in the code. For instance, the way particles seem to exist in multiple states until observed could be a way for the simulation to conserve processing power, only rendering reality when it's being observed. Critics, of course, argue that the simulation hypothesis is more science fiction than science. They point out that there's no direct evidence to support the idea and that it's impossible to test or disprove. Yet, the theory continues to captivate the imagination, offering a radical perspective on the origins of atoms and the nature of existence itself. As we reflect on this final theory, we're reminded that the quest to understand the universe's first atoms is not just a scientific endeavor but also a philosophical one. Whether we're exploring the aftermath of the Big Bang, the influence of cosmic rays, or the possibility of a simulated reality, each theory invites us to question what we know and imagine what might be. And with that, we conclude our exploration of the 30 theories about the universe's first atoms, leaving you with one final thought. What if the answers we seek are not out there in the cosmos, but written in the code of a reality we've yet to fully comprehend? As we bring this cosmic exploration to a close, let's take a moment to reflect on the incredible journey we've taken through 30 theories about the universe's first atoms. From the widely accepted Big Bang Nucleosynthesis to the mind-bending simulation hypothesis, each theory offers a unique lens through which we can view the origins of the cosmos. The diversity of these ideas is a testament to the boundless curiosity of humanity and our relentless drive to uncover the secrets of existence. Whether it's the role of dark matter, the influence of quantum fluctuations, or the speculative nature of multiverses, these theories remind us that the universe is far more complex and mysterious than we can imagine. What's truly remarkable is how these theories, while often conflicting, all contribute to a richer understanding of the cosmos. They challenge us to think beyond the obvious, to question our assumptions, and to embrace the unknown. The quest to understand the universe's first atoms is not just about science, it's about exploring the very essence of reality itself. And as we've seen, this journey is far from over. New discoveries, technologies, and ideas continue to push the boundaries of what we know, keeping the flame of curiosity alive. Now it's your turn to join the conversation. What do you think about these theories? Do you have a favorite or perhaps a new idea to add to the mix? Share your thoughts in the comments below. We'd love to hear your perspective. And if you're as fascinated by cosmic mysteries as we are, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an exploration into the wonders of the universe. Together, let's keep unraveling the mysteries of the cosmos, one atom at a time.